Alô, alô. Tá confortável. Ah, sim, claro. Pronto. Tá bom. Já tá ao vivo? Já tá ligado? Tá ao vivo, tá. É. Só... Opa. E aí, João? É o Google Groups. Então, eu pedi para o Henrique aqui agora só alguns anúncios novamente. O meu e-mail é esse daqui, tá? Meu e-mail. Me mandem mensagem para eu poder colocar vocês no Google Groups que eu vou criar da matéria. E se vocês quiserem também, me mandem o número de telefone para eu poder adicionar no WhatsApp. A gente cria um grupo de WhatsApp também para essa matéria. Aí, é isso aí. Ok. So, let us start with a quick review of what we talked about yesterday. So, we were studying the thermodynamic limit of the pressure for the Ising model. The Ising model is one defined by a family of functions on the configuration space, and this configuration space is just the -1 plus 1 to the power lambda, where lambda is a finite subset of ZD. And the model is defined by this expression. For each configuration, you assign the following value for the energy. Y for x and y sine lambda with a magnetic field where j, x, and y, hx are real numbers. Okay, and we actually, to study the pressure, we asked more. We needed these to satisfy more conditions. They should be short range. Short range, and this means that if there exists a positive R such that if the distance between x and y is larger than R, this implies that jxy is 0, okay? We also asked the translation invariance. Translation invariance. And this means that for any z, zd, the coupling constant x plus z, y plus z is actually equal to j xy. Notice that the translation invariance also means that the field in this part is constant. So hx equals h, as Kelvin noticed yesterday. And also we asked for another property that we called regularity. That means that the sum of j, x, y, y different from x should be finite. This is important actually for the long range case. For the case of a short range interaction, this is easy for a translation invariant and short range interaction. You just need to check this. Okay, so and this regularity actually puts a constraint on the decay of long range interaction that we will be talking about today. So we also defined a notion of boundary condition. So what is a boundary condition? A boundary condition is a configuration in the space, in the whole space of configurations. Remember this configuration space is just -1 + 1 to the power of ZD. And what you do is that you define the Hamiltonian with a boundary condition as being this Hamiltonian. This is the empty boundary condition, or the free part of the Hamiltonian. And you subtract a contribution from outside xy. But since the configuration is not here defined in every ZD, it's only defined on the finite set lambda, so you need to complete what happens outside, and outside you choose omega y. Okay, with the regularity assumption, even if you are in the case of the long range interaction, you can show that this is well defined. Sorry. Yeah, for every x. Yeah, for every x, if you don't have translation invariance, I guess. Yeah, you just need to check at the zero. At zero. Okay. Actually, for non-translation invariance, you need more. You need the supremum overall x to be finite. But yeah, and then the Hamiltonian it's well defined in this case because this since lambda is a finite set, the complement is always infinite. So this will be a series, and if you have this condition, you can show that this series converges. Okay, so yeah, and then we defined the first definition was the local pressure. The local pressure was defined as P omega lambda beta is a function of beta and h. Okay, remember this h is the same one as this h right here. Actually, today I want to make a small modification, because this will be useful when we talk about convexity today. I will also put another parameter in the Hamiltonian, the beta. I will just multiply this by beta. And why I choose this, it's because the beta is here and it's not here, so they are separated. So yeah, and it's more closely related to what Velenik did in his book. So, and this is the book that I'm following for this class. So okay. Okay, so this we need a beta here also. Okay, so what is the local pressure? The local pressure is 1 over the size of lambda. This is the number of points inside lambda times the logarithm of the partition function, and this is dependent on beta, h, and omega. And what is the partition function? The partition function is the sum over all the configurations, all the possible configurations of exponential of minus h lambda beta h. Oh, sorry. Beta here, omega here. So I put a beta here, so I need to put a beta here also, and here, to let the dependence of beta explicit. And since I did this already, I will put also the dependence of h here. So they all get explicitly, they appear explicitly in the definition of the partition function, okay? So what we were trying to do is to show that there is a limit in some sense for these functionals. Today, if we have time, it will be clear why we need to go to the limit. So first, we gave again a definition of convergence in ZD, because as you all can see, this gives me a family of local pressures depending on finite sets. So I need to give you a notion what I mean by convergence in ZD. So the convergence in ZD was defined in the following manner. You consider a family of finite subsets of ZD such that one, they must increasing. This means that the next one contains the former. Second, they must be invading. And what this means is that the union of all the sets in the sequence is actually equal to ZD. And the third property that I want them to satisfy is that they must go to this limit in the sense of Van Hove. They satisfy the Van Hove property, and this means that the limit of the boundary over its size, the limiting n, is actually 0, where, just to remind you, the boundary of a set is consists of all points inside this set such that there exists a y outside it with x minus y, and remember this distance is in the L1 norm. I will not write the 1 here anymore, okay? I wrote it yesterday, but I will not write it anymore, I mean, okay? So just to remember, if you have a box or a set like this, okay, so this is my set, lambda. So what is the boundary? I remember that ZD has a structure of a graph where I put an edge between every edge, every vertex that are nearest neighbors. So I actually have a grid like this. Okay, and then as you can see, in order to be in the boundary, it should a vertex should have an edge that goes right outside, and this guarantees the existence of something that is a nearest neighbor. So this vertex is in the boundary. This one is at the boundary also, and as you can see, I need another color. This one is not at the boundary. So what is the boundary set in this case? It consists of all these points right here. So this is the boundary of a finite set. Okay. So the theorem was there exists a number p for every beta h. There exists a number p, a real number, okay, such that for any sequence of finite sets converging to ZD, we have the limit of n plus infinity of p 1 by n omega beta h equals p beta h. And as you can see, the difficulty of this theorem is to show that these limits converge to the same thing for every converging sequence, and after that to show that the limit independs of the boundary. Okay, so what we did yesterday was to show the convergence for a very specific type of sequence. Let me erase my email. So we showed yesterday, that if you define dn to be 1 to the 2 power n to the power n to the power d, so this is a box with side length 2 to the power n. We show that for this sequence we actually have that we showed that for any m larger than n, the difference between the local pressure in dm beta h minus p, the local pressure in dn beta h, was less than a constant times 1 over 2 to the n minus 1 to the n. And this constant here only depends on beta, the dimension, and also something that we call J star, that is the supremum of this sum, or this sum. Okay, So this J prime is the important part of this result is that this constant doesn't depend on n, so we can take the limit. This actually proves that the sequence given by the local pressure for the boxes, these boxes, is a Cauchy sequence, so it must converge to some number, okay, that we call p beta h. So now we must show that for all increasing sequences, we have the convergence. So the second step is consider lambda n as in the theorem, as stated in the theorem, as stated before. Okay? So what happens is if I have a general set like this, okay, let me draw again. I guess it's better. So a general set. Lambda n. Remember yesterday that we not only defined the cubes, the n, but we also defined a family of translates, okay, given by you take something, a number in ZD, and then you translate it by summing every element in the n by 2 to the power n times y, okay? And we showed that this actually gives a translation, and the family, by translations, you can cover all your ZD, or all the ZD, or the lattice ZD, by disjoint sets. These translations actually make the cubes all disjoint, if the translation is different, okay? So what we can do is to cover your set with cubes like this one, but in another scale. Let's say in a scale k. And then this one. You see, not every one of them is a cube, but you understand it, okay? So you can cover it by cubes in any scale that you want. Let's say a scale k. And we will consider something, okay, I missed this spot right here. And we will consider the set lambda n. I don't recall what the name of this is. The bracket n. Yeah. As equals to the union. As I told you, every single one of these cubes is a translation of this initial cube. So there is always exists some some translation where I can write this cube as the translation of this one. So this is actually a union of y inside some set in ZD, some finite sets in ZD, and you take a union over all cubes that cover lambda n. But not only this, I will take A as a very special set. I want A to be the minimal one that covers the cube. So the minimal set where, let me write right here so you all can see. Where A is the set with minimal size, and by size I mean the number of points, okay? Such that this property holds. So, okay. So this gives us an approximation, and this is not the last time we will see this kind of argument. You are covering some set by cubes of a very large size. But okay, so what we will do is that we will show the convergence of the local pressure BH. Oh, just another thing. When I don't write anything here, I mean that I'm on the empty boundary condition case. Okay, the case with boundary condition I will talk about later. So I want to show that this goes to 0, to show that for any sequence it converges to this value. This value is defined as the one that this sequence converges to. And what I do is that I use the triangular inequality. So I first will approximate the pressure on lambda n, the local pressure, by the pressure in this set. Plus the pressure of this set by the pressure of the cube in the scale that I use to cover it. I call this decay, 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 plus P decay. Okay, so since beta and h are fixed right now, I will not write beta and h anymore, okay, until the rest of this proposition. So P. And notice that this inequality actually it holds for every case. So given an epsilon larger than 0, a positive epsilon, I know that there exists a k0 such that for any k larger than k0, I have p minus p less than epsilon over 3. Okay, so now we must analyze the other two differences. We will start by this one. And I will use, I will do this by first recalling that we have a decomposition property for H. Recalling the spatial decomposition property of the Hamiltonian. That means that if lambda prime are two finite subsets of ZD and they are disjoint, yeah, they are disjoint, then H lambda union lambda, the energy in the region composed by the union of these two regions, is actually equal to the energy inside lambda plus the energy inside the other region lambda prime plus a term that corresponds to the interaction between the regions. So this term is that we wrote like this, and by this we mean the sum of beta jxy sigma x sigma y, x inside lambda, y inside lambda prime. Okay? What we proved also is that we have actually a nice bound over these functions when you consider for every y different from y prime. We proved that dy k dy prime k, and for this we started writing y prime to not to get a better notation, right? So we proved that this was actually less than a constant c times 1 over 2 to the power n plus 2 d minus 1. This is what we showed, and this constant is independent of n. But it's dependent on the range, okay? So now we have can I erase the theorem? What do you think? Okay, so what happens is that for this pressure in the let's say in the cover of lambda n by the cubes, I know that they decompose into, since the cubes are disjoint, they decompose. They can be yeah, they decompose as, you can use the decomposition property to show that this is actually equals to the sum over y inside A, where A is this minimal set right here of h dy k plus the sum over y different from y prime inside A of lambda y, oh lambda, sorry, w y prime. the first thing that I want to say is that since we are studying the limit, okay, and the interactions are of finite range, I can always assume, okay, that the n, or in this case the k, the scale of the box, is so large such that the range of the interaction will always be contained in this neighborhood. Okay, so what I mean is that the size to n is much larger than r. Okay, so there is no interaction between, there is no interaction term between this cube, let's say z, and this cube right here. They don't interact, meaning that they are much farther apart. So this will be 0 every time I have every time they are very distant. So okay, what this implies is that assuming two to the power n is much larger than r, we have that k, yeah, exactly. Sorry, thank you. Inside A, okay, I can show that this will be okay, so this will be y over A and summing over y prime different from y, such that the distance is less than 1. Okay, they are in a neighborhood. They are in the neighborhood. Actually, it's not exactly that distance, because the distance in the L1 norm is something like this. But the interaction can interact with the cubes in this region. So to have an actual cube that I can write in a distance, I should use the supremo norm. So then I will write like this, where the supremo norm is defined as the supremum, or in the case the maximum, since it's a finite set, okay, of E, D, X, Y, okay. And you can see that this ball is actually will be this ball will actually be a cube. So y prime sigma, okay. If I take the absolute value here, and I have already this this upper bound right here. Sorry, is in the numerator. I guess it. Oh, it's in the numerator. Yeah, like this, right? D minus 1. Yeah, thank you. So now we use this this inequality here over here, and we get so let me enumerate the inequalities. This will be 1, and this over here will be 2. So using 1 and 2, we have the sum of w y y prime, the absolute value of this sum is actually less than the size of A times the ball in the supremum norm of radius 1 have at most 2 to the power of d. I guess it's easy to see this. And times this value over here. So the constant times c times 2 n plus 2 d minus 1. Okay. Now we plug this inequality. I don't want to erase this, don't want to erase the drawing, so I will erase this property here. So, okay. Now we have that inequality. This implies that the last inequality implies that H in the cover of the finite set lambda n is less than the sum over y in the cover of H dk y. These terms right here, right? Plus the upper bound that we have is A times, okay, so we will make a deal right now because I don't want to enumerate every constant that I get. So since 2d is a constant that only depends on d, I will absorb this into c and I'll not write it anymore because it doesn't matter, okay? So c times 2n plus 2 d minus 1. Okay, and the same thing to the other side. Actually, not the same thing, but something related. The sum y sigma, this time minus A times C times 2 n plus 2 d minus 1. Now I take the exponentials. The exponentials will preserve this chain of inequalities. So this implies that this term here is less than the exponential of A times C times 2 to the power n plus 2 d minus 1, okay, times the product of y in A of the exponential of minus h d k y sigma. And to the other side, I get the same thing. Again, not the same thing, but something similar. A times C times 2 to the power n plus 2 d minus 1 times the product of y in A, the exponential of minus h dk y sigma. Okay, so the next step is I need to get the partition functions, since this inequality holds for all configurations. Then I just sum over all the configurations, summing over all configurations, summing over sigma inside the configuration space. I get here in the middle, I will get the partition function in lambda n, in the cover of lambda n, will be less than the exponential of a times c to the power, okay, 2n plus 2 d minus 1 times the sum over the configurations. And now I have a product dky sigma, and something closely related to that here. The product ya exponential of minus h dk. Okay, I need more space. C2n plus 2 d minus 1 times the sum over all the configurations of the product y in a of the exponential of minus h dky sigma. Okay, so this and this. Now what we do is that we split, okay, here is our configurations inside the cover, here is the configurations inside the cover of lambda n. So what we do now is that we want to interchange the sum with the product. So what we do is that we split this sum according to the configurations varying over the subsets, since this forms a partition of the set. And then we can, after doing this, we can interchange the sum with the product in the following way. This will be the product of y over a, of y in a, times the sum, okay, a product of the sum of the configurations that only vary over dky exponential of minus h dky sigma. Okay, but again, this is exactly the expression of the partition function over dky, and since the interaction is translation invariant, this is exactly as equal to the partition function over dk without the translation. So what we get is yeah, exactly. Thank you. So okay, so this is a product of the size of a terms that are equal. So this will be exponential of minus a times c times 2 to the n plus 2 d minus 1 times the partition function of zd to the power a yeah, exactly, is less than z, the partition function in lambda n, in the cover of lambda n, a times c times 2 n plus 2 over d minus 1 times the partition function to the power a. Okay. So now we take the logarithm of everything. The log will also preserve the inequalities. And then we divide by the size of the set. Okay? So after taking the log, taking log and dividing by the size of the cover, we get this part. We get the local pressure here in the cover of lambda n, and this will be, let me do first the upper bound. The lower bound will be the same. Okay, it will be yeah, it will be almost the same. So this will be less than the logarithm a times the logarithm of the partition function in the cube decay, in the box decay, over the size of the cover lambda n plus a over the size of lambda n times c times 2 n plus 2. Actually, again, this is not n, this is k, because the bound that I'm using comes from the interaction between the cubes, so this is k. Okay. K, 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 K. Okay? Okay. Otherwise, it would go wrong, right? Okay, so dk plus 2 over d minus 1. Yeah, so this is everything. So what is the size? What is the size of lambda n? Well, the size of lambda n is the number of the cubes, because it's a union of disjoint cubes. So it's the number of cubes that I have times the size of the cubes. And and I have exactly a cubes. So this is a times the k. And what is the k? The k is 2 to the power k. 2 to the power k d. Right? Right. So what we do is that now we plug this over here, and we have that the partition function, the pressure, the local pressure, is less than log of the partition function over the cube dk. Now the size of a here cancels out with this size of a, remaining only the volume or the size of the cube dk, dkd, and this is just the partition function of dk. Oh, no, sorry, the pressure, plus the a also cancels out, and it remains c times 2 k plus 2 d minus 1 over 2 k d. Okay, so again, I don't need to consider this 2 over here, because this is actually 2k d minus 1 times 2 to the power 2 d minus 1. Okay, so this is also a constant. This is a constant that only depends on the dimension, so I will absorb it right here. So this gives us that the pressure is less than the pressure in the cube, in this cube, dk, plus a constant c. Again, this constant now this term is absorbed into this constant right here, times over 2k, over 2k, right? And a similar trick works for the other part, for the lower bound. So what I conclude is that the difference between this pressure minus PdK is less than a constant that doesn't depend on K and N over 2 to the K. Okay? So in this case, I know that there exists a K1, such that if K is larger than K1, then C over 2K is less than epsilon over 3, where this epsilon is this epsilon right here. Okay? So all I need to do to make this this work is to take K larger than K, some K larger than than the maximum of K0 and K1. And now the last part that I need to control is this one. So let me write with what we just proved. So therefore, if K is larger than the maximum between K0 and K1, we have that the pressure in lambda n minus the pressure, this value over here, is less than 2 epsilon over 3 plus the difference between the pressure, the local pressure in lambda n minus the pressure in the cover. Now we need to analyze only this last term. So, okay. Since this set over here is a cover of lambda n, it contains lambda n. So we can write, we will write lambda n as being the union of two disjoint sets. So it will be lambda n with the union of lambda n minus, the cover of lambda n minus lambda n. And this set over here we will call delta n. So let's go back to this drawing that I didn't erase. The orange part is the cover. The orange part is the cover. But the real set is the set in white. Okay. So what is lambda? What is delta n in this case? Delta n will be the difference between the cover and the set that it contains. So it will be this region over here, the green one. Okay, so if the set lambda one is, lambda n is the white set, and the orange set is the cover, then the remaining part, delta lambda, is the green one. So okay, so what's next? So we decompose the Hamiltonian in the cover as the Hamiltonian in lambda n plus the Hamiltonian in delta n plus w lambda n delta n. Okay? So let us take a look first to this term right here. So what is this? This is the sum over x and y inside delta n, jxy, sigma x, sigma y, plus the sum over x inside lambda, h, I have a beta over here, h, sigma x, okay? Delta n. So if I multiply this by 2, okay, and divide this by 2, I can transform this sum instead in a sum of subsets of 2 points inside here. I can transform this sum as a sum. I can write this sum. So since sum over lambda n and the sum over jxy sigma x sigma y is actually equals to 2 times jxy sigma x sigma y for the sets right here, okay? Okay, I'm just taking here I can have repetitions because here I'm summing x and y and x, okay? So and in this sum I don't have a repetition. So since this holds, I can write the Hamiltonian as being a sum over x inside delta n of a sum of y delta n, okay, of jxy sigma x sigma y plus hx sigma x. Oh, h sigma x, because h is constant for us. So what is the absolute value? I can use that this is less than the sum over x inside delta n times the sum over y delta n jxy plus h here, okay? And as we saw, this is actually a finite sum because of regularity, okay? As we talked earlier. From here to here, yes, exactly, because here you have 2 times the sum, so you actually have half here. Yeah, exactly. So I can put over 2 here. So this will give us, this is less than, by regularity, this is this is a constant, so I can bound this by a constant. So this is sum of x in delta n times j star over 2. Let's say there is a bit over here, a bit over here, a bit over here, a bit over here, because there is a bit over there also, plus h. But this is a constant, and I'm summing every point inside delta n. So this will be a constant, beta j star over 2 plus h times the size of delta n. A similar bound holds for the term with the mixed term interactions, the W term. So what we get at the end is that a similar bound holds for W, a similar bound holds for W lambda n delta n. So we have that the Hamiltonian inside the cover will be less than the Hamiltonian inside lambda n plus 2 times the constant that we just arrived. So 2 times, so beta j star plus 2h, the size of delta n. And a similar lower bound, just changing the sign of the constant. So you put them in a sign over here, 2h delta n. Okay? Again, we do a similar trick. You take the exponential and you sum over all the configurations. So you get here the partition function that will be less. I will do just the upper bound because the lower bound is similar. So you take the partition function that will be less than the exponential of beta j star plus 2h times the size delta n times the sum over all the configurations in the cover here times the exponential minus beta h. Oh, there is no beta here, just something like this. Okay. So what happens is that there is still a problem because the sum is over all the configurations in the cover, but I only have the Hamiltonian in the finite set lambda n. So what I do is that I can split this sum again as a sum over configurations inside as sum over configurations inside delta n, and after that summing over all the configurations inside delta n. And now I have something nice because this will be the partition function. This will be the partition function. And then I have that this will be equal to, since the partition function is equal, I just need to count how many configurations I have in this set over here. And since we are in a situation where we only have plus or minus spins, the possibilities are only, all the possibilities of configuration are just 2 to the power of the size of delta n. So this will be equal to, this over here will be equal to E B J star plus 2H times the size of delta n times 2 the size of delta n times z lambda n, the partition function of lambda n. Now you take the logarithm, and then you have that the logarithm of z in the cover minus the logarithm of z in the set lambda n is actually less than beta j star plus 2h times the size lambda delta n. And since I can do a similar bound to the other side, but with changing the sign right here, this gives me actually this inequality. But you see, this is not what we need, because we need to control this term right here. So to control that term, to finish the proposition, so notice that p lambda n minus p lambda n right here, this is over this set, 1 over the size of the cover, logarithm of the partition function. Now I sum and subtract something special, and it will be it will be this 1 over the size of the cover. But now I take the logarithm of z lambda n plus this term that I just add. So this adds up to 0. Lambda n minus 1 over lambda n log z lambda n. Now, taking the absolute value and the triangular inequality, the absolute value of this is less than the absolute value of this, plus the absolute value of this. Okay? Yeah. Yeah, I can erase this part. So this part right here, I can put it in evidence this this term that is dividing the log. So this is actually this part right here in orange will be equal to 1 over lambda n, the cover lambda n times the difference, the absolute value of the difference, okay? And by using this inequality, I have that this term is less than beta j star plus 2h times the size of delta n over the size of the cover. Notice that there is nothing in this inequality that I gave to you, that I deduced it here. There is nothing special in the set delta n. I could have made the same argument, but changing delta n by any finite set. Okay? Do you agree? So this means that I have this inequality here, beta j star plus 2h times the size of lambda n. This implies that the partition function z lambda n, that is the sum over all configurations actually I forgot a constant somewhere, because there is a 2 over here. You can see there is a 2 over here. So this is actually the exponential of log 2, and then I need to add log 2 here and add log 2 here. And I will call all this constant just k. So just add log 2, and this will be big K. So this will be the exponential of minus h lambda n sigma. So by using this inequality right here, I have this is less than the number of the configurations inside lambda n. This is just 2 to the power of lambda n times the exponential of 2h plus beta j star times lambda n. And again, this will be less than exponential of k times the size of log n. So if I take the logarithm of the partition function, I have this inequality here. This will be less than k times the size of the set. So why I need this? Because now I have this other term right here that I will put in green. No, I will let this part to finish the proposition. Okay, so the green part, the green ball over there is equal to 1 over lambda n minus 1 over the size of lambda n of the cover, right? Because this is the absolute value, and this set is contained in this one, so this term right here is positive, times the logarithm of the partition function that we just derived this bound right here. So we can actually have that the green ball over there is less than this times k, big K, times lambda n. This gives us k times 1 minus lambda n over the cover, but this is k times the size of the cover minus lambda n over lambda n. And as you can see by the definition of delta n, this is exactly the size of delta n. So this part over here is exactly the size of delta n. So what I got at the end is that this part over here is less than 2k, because I have one term k here and another term k here, times delta n over lambda n. Of course, in this part I have the size of the cover, but since the size of the cover is larger than lambda n, then this is an upper bound to that part. So now we need to finish. We need to analyze 2 over 3. We need to analyze what happens to this part over here. So first, I erased the drawings, but what happens is if a cube, if a point is inside delta n, then it is not contained. It may not be contained inside lambda. So, okay, mini drawing right now. So I have this set. This will be lambda n. And I cover it by cubes. Okay, this will be the cover. And then lambda n will be this set over here, the green one. The green one over here. So if the cube is not completely contained inside lambda n, then it will certainly contain a point at the boundary. Okay? So every point at the boundary of lambda n, every point of the inner boundary is contained here in lambda n. Okay? But for the worst case scenario, of course this doesn't happen, is that if I had so in the worst case scenario, you only have one point in each cube. Of course this is impossible to happen, okay, but since this is a cover, the worst case scenario is that I have each cube covering only one point of the boundary. Okay? So in this case, the set will be, in this impossible situation, at most the size of the cube, all of the points of the cube, times the number of points at the boundary. So this will be at most the number of points at the boundary times the number of cubes. Again, because every point at the boundary of this set is in this region right here. Okay, is in this region right here, and since this region is also contained in the cover, it is composed by cubes. So in the worst case scenario, you only have one point of the boundary inside that cube. So it will have at most, in the set, at most the size of the boundary times the k. Okay? So, but now remember that we took k large than k0 and k1, but fixed. So we can take now the limit in n And since we know that the sequence converges in the sense of Van Hove, this means that there exists a big N such that for every N larger than this big N, we have that times dk. This is a constant because k is fixed. This will be less than epsilon over 3, and then the proof is over. So there exists the limit, and the limit always is it is always that p that we constructed yesterday. So okay, some consequences of this proof. Consequences of this proof. The first one is since the Hamiltonian with boundary condition is written as the Hamiltonian with empty boundary conditions plus some term, omega y, and the interaction is regular. We know that this term over here is actually less than the size of the box times a constant. Let us call it bj star. Okay. So what this means is that by the same argument that we did before, this implies that the pressure in a finite volume with empty boundary condition is less than okay, actually there is we need to have a little more care with this. So because I don't want the volume here. So what happens with this case is the following. So you have jxy, this term right here. And let us consider every finite box, okay? So again, since this is finite range, okay? We are in the finite range regime. So this is actually less than the sum over outside a ball of radius r for each x. Okay, so this is the side, the box lambda. Since this is a sum that depends on the inside and the outside, okay, we cannot have as lambda goes to infinity, as lambda n goes to infinity, as lambda goes larger and larger. At some point, these pairs will be distant. So in that case, j will be less than. Actually, it will not be less. It will be equals to 0. So this sum can actually be upper bounded by j star. This is the supremum of this times the number of pairs xy inside. One x is inside lambda and the other one is outside, such that x minus y is less than or equals to r, where r is the range of the interaction. But again, by a similar argument that we did yesterday, but a similar argument, that we did yesterday. We know that the number of pairs, this number of pairs that are one inside lambda and the other outside lambda c, such that x minus y is less than r. This will need to be less than a constant that depends on r, times the boundary of the set. Okay? And now, by using that inequality, we can remake the argument that we are doing here to control the difference of the pressure. Let us call this constant CR. So we actually have the partition function of with a boundary condition, beta h. If we take the log, the partition function, this will be between two quantities. One will be exponential of CR times the boundary of lambda n times the partition function with empty boundary conditions, and a similar thing right here. Beta h. Now you take the logarithm and divide by the size of n. What we get is that the difference between the pressure, the local pressure with empty boundary conditions minus the pressure with boundary condition, beta h, will be less than a constant that depends on r times the size of the boundary divided by the volume. So again, by using the fact that this sequence satisfies the Van Hove property, we get that these sequences are converging to the same place. So the pressure doesn't depend on the boundary condition, but more can be said. If I add any term f lambda sigma to the Hamiltonian, to h plus lambda sigma, okay, such that f lambda, the sum over all the configurations here is less than some is. Are you okay with O notation? Is better not, right? So okay, so if this is something that, okay, I know what to write. So such that, let's put an n here, and then let's say that the sum divided by n, the limit is 0, okay? This means that this part over here loses to the contribution of the volume. Then the pressure, then the limit, the pressure by a similar argument of the system with this Hamiltonian plus this term will be the same as the pressure of the system with only this term. So why this will be important when we show phase transition, when we are studying phase transition. But an important example of something that does that behaves like this, something that behaves like this, is decaying field. It's a decaying field. So what is the decaying field? The decaying field is defined by the following. I take a magnetic field, Hx, that is given by some H star, a constant, positive, and I divide it by x, and I take it to the power delta, where delta and H star is positive. It's positive. We will show later that that if I add a contribution to the Hamiltonian, if I add a contribution to the Hamiltonian that is similar, that is equals to this part over here, to the Hamiltonian, at something like this, then the pressure without the volume, without the field, is equal to this one. Then the pressure will be equal to the one without the field, without the decaying field. Why this matters? Because you have very different behavior when you are studying a phase transition on the level of the functions of the Gibbs measures. When you are studying the phase transition in this context, you have very different behaviors when you vary these parameters, delta and H star. Some parameters even we don't know what happened. So okay. Any questions on this part? No? So, okay. What I wanted to do is, how much time do I have? I have 15 minutes. So what I wanted to do is to talk a little bit more about the pressure and the relation with the Gibbs measures, but I guess it's too late right now. What I will do is use the remaining time to show that we can, because what we did here is to show that the pressure exists for finite range Ising models, but what about the long range Ising model? And this is the one that the name long range is in the course. So how do I show that the pressure exists for the long range model? So what about the long range? Well, for the long range, the trick is to use a truncation. Okay. So what you do is that you start start with lambda n converging to ZD, and a long-range Ising model. What we do is the following. We want to show that the pressure here forms this sequence here. We will show that this sequence here is a Cauchy sequence. So what we need to do? Let us take a look again to the Hamiltonian of the Ising model, but now only to the part that have a two-body interaction. So let us take a look to this part right here. JXY, okay? JXY times sigma x, sigma y, xy here inside lambda. So I can break this sum into two sums. The first one with a restriction. I only sum the pairs such that x minus y is less than a number r, and I sum the remaining part right here. X minus y larger than r. xy sigma x, sigma y. Well, by just readapting oh, sorry, I have a sigma x, sigma y here. By just redefining the interaction, this part is similar to a finite range interaction, okay? But what about this part? Well, this part right here, I have the following. The absolute value is less than, again, the sum of x in lambda, and I sum here half y in lambda such that x minus y is larger than r, jxy in absolute value. But again, I asked you that the interaction should be regular, okay? And if you remember the definition of regular, I asked that this was true. In this context, let us consider translation invariant. I asked this, okay? So since this series converges, what this means is that this series right here, okay, this term right here is actually less, since this term right here, y inside lambda, x minus y than r, is actually less than if I consider every y different from x. Now I have many more points than the points that are only inside lambda, and then I take just x minus y. 0, y. Okay? And since this series converges, this means that this series over here this is the tail of this series. So this is actually a constant CR, that goes to 0 as r goes to infinity. Again, because this series converges, okay? So this term right here will be less than the size of the system times the CR over 2. And what we have now? Let us call this Hamiltonian here the short range approximation of the Hamiltonian. We say that the Hamiltonian with this part will be h lambda r. And the Hamiltonian with this part right here will be h lambda, the truncation. So what we did implies that h lambda sigma is less than h lambda r, lambda r sigma plus lambda CR. And this implies that the pressure of the system, by the same argument we did before, will be less than the pressure of the system with this finite range R, okay, plus lambda, the lambda will get divided, so plus CR. Since this similar bound holds, this implies that the difference between the two are less than CR, and this is independent of the box lambda, okay? So what this means for the case, to show how we use that to show that this is a Cauchy sequence. We have that P lambda n minus P lambda m. This is the local pressure for the long range model now. This will be P lambda n minus P lambda n r plus P lambda n r minus P lambda n lambda m r plus P lambda m r. Okay, so this is 0, minus P lambda m. So by taking the absolute value and using the triangle inequality, we get this. But we showed that for any lambda this holds, okay? So this term right here and this term right here will be less than CR. So since I have two of these terms, I have 2 times CR times the pressure right here. But the pressure for a finite range model is converges. So for any epsilon that I take, so this means that for any epsilon positive that exists an n such that if nm is larger than n, then this implies that P lambda n r minus P lambda n r is less than epsilon. But again, now this holds for any r, and r goes to 0. So this implies that P lambda n plus P lambda n is less than. So this shows the existence of the pressure also for long-range Ising models. And okay, I will stop here, but what we will do tomorrow. So tomorrow we will start the study of the proper study of the Gibbs measures. I will show why the pressure is important, how the pressure relates to the probability measures known as Gibbs measures, and then we will show maybe the uniqueness with a field that is different. So I see you tomorrow. Sorry? Yeah. Of the Gibbs measures, yeah. Yeah. Okay, maybe a few words before we finish. What happens is that now we defined the thermodynamic limit of the pressure. If you see every finite volume pressure, the derivatives exists in beta and h to any power that you want. You can calculate it by hand. So we were trying to find a bad behavior, some kind of bad behavior. So what they did in the beginning of statistical mechanics, actually before the mathematicians arrived to the area, is that they defined the pressure and then they tried to calculate the pressure exactly. And then when you calculate the pressure, as you know, even if the derivatives exist for every point in the for every point of the sequence of functions, it's not true that the limit will be differentiable also. So what they did is define the pressure, try to calculate the limit, and see that in the end what happens to the derivatives. And it turns out that, I guess, since the 40s, we don't have much action in calculating explicitly the pressure for Ising model. We have the calculation of the pressure, exactly the calculation of the pressure for the one-dimensional model. We have the Onsager solution that's in the 40s for the pressure in the two-dimensional Ising model with zero field. And after that, nothing. We don't. There is no proof. There is no exact computation of the pressure, even in the two-dimensional model with a magnetic field that is not zero. But for dimensions 3, 4, and over, we don't know how to do it. So in order to study phase transition, you can't rely on exact methods to calculate the partition function, because it's too hard, and many physicists think that it is actually impossible to calculate in dimension 3, for instance. So you need another way to study phase transitions, and this way will be through the Gibbs measures. And tomorrow we will discuss it, how this relates to the pressure and statistical mechanics. So now if any more comments? Okay. Acabou. Corta, claquete. Corta. Deixa eu desligar.